Hello, everyone, and thanks for listening to this presentation. I'm Lucas from KaiPAC at Stanford University, and I'm going to present part of the Extragalactic Magnetism with SOFIA legacy program. Specifically, I'm going to present the result on the Circinus galaxy of tracing the magnetic field in this central region. So as I was mentioning, this is part of the SOFIA legacy program led by Enrique Lopez Rodriguez and Anne Mao, which aim at measuring a magnetic field in nearby galaxies thanks to SOFIA in the far infrared. If you want to have more information, you can look at the other talk of the team or look at the website. And so my contribution to the project is looking at one specific object, which is the Circinus galaxy. So it is pretty well known that the central region of active galactic nuclei is very complex, as can be seen on a recent sketch by Izumi et al. In 2018. And in this game, magnetic fields are known to play an important role, but their exact contribution and role is still poorly constrained, and so we need more observation to actually constrain this exact role of magnetic field. And this new galaxy is one of the closest active galactic nucleus, and is such very good targets to try to map this magnetic field, since with only 4 megaparsec away from us, one arcsegon represents 20 parsec on the galaxy. So this allows actually to get pretty high spatial resolution of this object and to try to better understand a magnetic field on this object. So I'm going to first speak a little bit about the specificity of observing magnetic field in the far infrared, thanks to the Oculus instrument on board SOFIA. And I'm going to present then the observation we obtain thanks to that, specifically the polarization maps and the azimuthal profiles we extract from them. We then compare these profiles to magnetic field model in order to constrain the structure of the magnetic field we're observing in these images. I'm sure you know like how to observe magnetic field, but depending on the wavelengths, we are actually facing a slightly different problem. And the good advantages of observing the magnetic field in the far infrared is that we are not very sensitive to either synchrotron polarization, absorptive polarization, and scattering by either dust of electrons. So we are only dominated here by emissive polarization, which is pretty helpful because that allows, if we have like a strong enough magnetic field that align the elongated grain in the medium, this is going to emit preferentially in polarization in the direction 90 degrees of the direction of the magnetic field. And so we can trace directly the direction of the orientation of the magnetic field by just rotating 90 degrees the polarization we are detecting from these sources. So for this reason, in the rest of this talk, all of the polarization vector I'm going to present are already rotated by 90 degrees to match the orientation of the magnetic field. So this is one example. So this is an observation we obtain thanks to Oculus on board SOFIA. So the left side shows the A band map at 53 microns. The central band is the C band is at 89 microns. On the right hand side is the E band at 214 microns. The first row shows the total intensity, while the second row shows the polarized intensity, and on all of them you can see the polarization vectors, which are overplotted with the lengths depending on the polarization degree, and the orientation rotated by 90 degrees to map the magnetic field orientation. So it is important to note that because in all of these different bands, we are not having the same field of view and not the same beam size or not the same resolution, we are also not exactly probing the same scale on the object. Furthermore, it's also interesting to compare that with already observed, for example, a map from the CO from ALMA from Kawamura et al. 2019. Specifically, if you look at the velocity map in the center, we can see like the polarization orientation of the magnetic field is exactly on the equatorial plane of the galaxy, as shown by the rotation of the interior structure. And so we are going to try to constrain the structure a little bit better. So in order to do that, we compare this observation with a three-dimensional axis-symmetric magnetic field model defined by 6 parameters. I'm going to explain here a little bit more in detail. So first, the inclination of the entire structure on the line of sight is pretty straightforward, and then we also have the tilt angle on the plane of the sky of the entire structure. Then the polarization level tells like the maximum polarization we are observing for the model. More interestingly, the pitch angle represents the which is the orientation of each vector compared to the center. So if the pitch angle is 0, that means that all of the vectors are aligned in a circle around the center, as actually can be shown in this example. But if the pitch angle is non-zero, is actually going to draw a spiral pattern around the center. And so these are the main parameters we're going to focus on in the following, because the two vertical parameters, which are the vertical extension and the vertical pitch angle, are way harder to constrain because our model is based on an edge-on view and is just pretty non-sensitive to these parameters. But they are like pretty interesting to visualize because they are showing us this view, which is based on the most on the best parameters we obtained for the magnetic field on the Circinus galaxy. So the right-hand side is a view of the magnetic field we get from the best fit parameters on the actual orientation of the Circinus galaxy on the plane of the sky, while the two middle and left part are showing the face-on view and an edge-on view of the same magnetic field model. So to get to this point, we have fitted like these 6 parameters I've been describing earlier on. And despite some degeneracy, and specifically the 2 vertical parameters show a pretty low constraint on their respective values, we have a pretty good agreement and a pretty well-defined 4 other parameters. As you can see, so the black points are the azimuthal profiles we get from the observation. The purple line is the model if we impose the same set of parameters to try to represent for the 3 bands at the same time, which is working reasonably well. But if we allow the parameter set to change for all of the different wavelengths, which means that also we are proving different scales, the fit is more successful and have better quality to fit the profiles. So the first line is the polarization degree, and the second line is a polarization position angle, and all of that is depending on the azimuthal angle surrounding the very center of the AGN that we have been removing from the data. And so if we look at the best parameters we have obtained, specifically the variation depending on the wavelengths, it's interesting to note first on the right-hand side the inclination, which if we go to shorter wavelengths, so to the A band, that's probably also like smaller scale, closer to the very center of the galaxy, we are seeing the structure more and more edge-on, which is compatible with what is actually known for the Circinus galaxy. And then another interesting factor is the pitch angle we are observing, which for the smaller and larger scale are between -20 and -30 degrees, which shows pretty like spiral pattern. While in the intermediate scale, the C band, we are observing value closer to 0, which is with -8, which shows a tighter spiral pattern closer to a circular pattern. So this is interesting because this happens at scale around 200 or 300 parsecs. So as you can see on the right-hand side, that the pictures we are observing from this work, and on the central part, on the intermediate scale of 200 300 parsec, we are observing more circular orientation of the magnetic field, which actually correspond to the location of the circumnuclear disk or ring, depending on the authors, which are shown on the left-hand side in the Oshuga and Umemura work in 2001. It is actually clearer if we look at the Izumi et al. Map, CO map from 2018, where we can actually see the end of the spiral arm reaching the circumnuclear disk in the blue line on the right hand side, and then also known feature of inner spiral at the very inner part of the circumnuclear disk, which would be actually what we observe in the A band. So the work on the Circinus galaxy analysis is pretty much done now. So the paper will be submitted pretty soon. But you can stay tuned for more information about like possible simulation we are going to conduct on magnetic field, but also about other galaxies we have already observed and we are going to analyze in the future through the SOFIA legacy program, specifically Centaurus A and AGC 1068, for example, already published, but there's a lot of other AGN coming on. You can have a look to the other talk of the team. So Enrique Lopez Rodriguez is going to present the entire program, and Cham and Gokli and Alejandro Borlaf are going to present two different aspects of the M51 galaxy. Thanks for listening, and I'm gonna stop here with a brief summary of the talk. Thank you.